Hello students, I am Dr. Yasha Tayal from ABES Engineering College. Today we will discuss superconductivity and nanomaterials frequently asked question. So very important question from this chapter is a long thin superconducting wire of metal produces a magnetic field of 105 into 10 power 3 ampere per meter on its surface. Due to current passing through it at a certain temperature T Kelvin, calculate the value of this T temperature. So given is critical magnetic field at 0 Kelvin and its critical temperature is given 9.3 Kelvin. The formula we're going to use for this particular question is HCT is equal to HC0 1 minus T by TC whole square. So in this question, HC0 is given 150 into 10 to the power 3 ampere per meter. TC is given 9.3 Kelvin, while HCT is also given 105 into 10 to the power 3 ampere per meter. You can also guess the value of HCT. HCT should be lesser than HC0. So when you will substitute this value in this above equation, you can determine the value of T. So we can write here 105 into 10 to the power 3 is equal to 150 into 10 to the power 3, 1 minus T by 9.3 square. So when you will solve, this will cancel 105 by 150, 1 minus T by 9.3 square. On further solving this question, you can obtain the value of T by this as 105 by 150, 1 minus this. So when you solve this value, T value is found to be 5.03 Kelvin. So in this, you have to determine the temperature at which 105 into 10 power 3 critical magnetic field value was given. So it's a direct formula based question. Next important question from this chapter, which is frequently asked, is for a specimen of vanadium gallium critical magnetic field. So there are here two critical magnetic fields are given. HC1 is 0.176 Tesla. So this is given at 14 Kelvin. So this is your T1. While HC2 is given 0.528 Tesla, which is provided at 13 Kelvin, which is your T2. Here critical temperature is given. You have to calculate the transition temperature and you have to determine the critical magnetic field at 0 Kelvin. And you have to also determine the critical magnetic field at 4.2 Kelvin. So this is basically T2 here, and we have to determine this at T3. So in order to solve this, we will build the equation on the basis of a standard formula. HCT is equal to HC0 1 minus T by TC whole square. So first we have the equation 0.176 is equal to HC0 1 minus T given as 14 by TC whole square. This is our first equation. Second, 0.528 is equal to HC0 1 minus 13 by TC whole square. This. So when you will divide equation 1 and 2, so HC0 will cancel and you will get the equation as 0.176 divided by 0.58 is equal to 1 minus 14 by TC whole square divided by 1 minus 13 by Tc whole square. So on solving this, we can find the value of Tc, which is found to be 14.5 Kelvin. We can solve this. Now in any of the one equation, let we substitute in equation 1. In equation 1, we will substitute the value of Tc. So 0.176 Hc0 1 minus 14 by 14.5 square. So when you will solve, the value of Hc0 can be observed to be 2.588 Tesla. So this is the second parameter which is determined. This is a very important question. Frequently asked. This was the first parameter. We have determined value of Tc. Now we have to determine the critical magnetic field at 4.2 Kelvin. We have to determine this value. So again, we can calculate HCT. We have the value of HC0, 2.588 into 1 minus. Now our T is 4.2 and our critical magnetic field is 14.5 square. So when we will solve this equation, our value is found to be 2.3 Tesla. So you can see as the value of temperature is reduced, magnetic field is decreased. At 4.2 Kelvin, the value is further decreased. It is 2.3 Tesla. Okay? In previous, it was 2.58. From 2.58, it was 2.3, and HC0 was 2.58, and that for value at 14 and 13 Kelvin, it was these. Right? Moving over to the next question. This is again an important question. Transition temperature for lead. So in this question, Tc is given as 7.2 Kelvin. At 5 Kelvin, it loses superconducting property subjected to a magnetic field of, so here T is 5 Kelvin, and at this temperature, magnetic field is 3.3 into 10 to the power 4 ampere per meter. Find the maximum value of magnetic field which allow the metal to retain its superconductivity at 0 Kelvin. So maximum value of magnetic field is actually the magnetic field at 0 Kelvin. So again, we need to write the standard formula first. HCT is equal to HC0 multiplied by 1 minus T by Tc whole square. So here HCT is given. We have to determine HC0. So HC0 will be 3.3 10 to the power 4 divided by 1 minus T is 5 Kelvin, Tc is 7.2 square. So on solving, the value which is obtained is 6.37 into 10 to the power 4, unit is ampere per meter. I hope so this question is also clear. Next important question which appear in university examination is where to determine the transition temperature and critical field. We have to determine HCT when temperature is 4.2 Kelvin. What are the parameters given? Critical field HCT1 is given to be 1.41 into 10 to the power 5 ampere per meter, where T1 is 14.1 Kelvin. Again, HC is given, C2 is given 4.205 10 to the power 5 ampere per meter, when T2 is 12.9 Kelvin. Temperature is reduced, so your magnetic field will be increased. So we can develop two equations for the same from this standard equation. HCT is equal to HC0. We always need to write the basic equation. 1 marks goes for this standard equation. So first equation, we will have 1.41 10 to the power 5 is equal to HC0 multiplied by 1 minus 14.1 by TC whole square. This is similar question which I discussed previously. We'll develop two equation. Again, 4.205 10 to the power 5 is equal to HC0 1 minus. Now this is 12.9 by TC square. This is our second equation. If we'll divide these two equations, HC0 will cancel out. We will have 1.41 divided by 4.205 is equal to 1 minus 14.1 by TC square divided by 1 minus 12.9 by TC square. So on solving this, the value of TC which is obtained in this question is 14.67 Kelvin. So this is the first parameter which we have obtained in this numerical. Now next we have to determine here magnetic field at 4.2 Kelvin. So in order to determine magnetic field at 4.2 Kelvin from this particular formula, we need to know the value of HC0 also. So we will substitute the value of TC in equation 1 and we will determine the value of HC0. This can be determined as 1.41 into 10 to the power 5 divided by 1 minus 14.1 by TC is 14.67 square. So this value is found to be 18.455 into 10 to the power 5 ampere per meter. So we will substitute this equation into our this basic equation. We have determined the value of HC0. We have determined the value of CT. So when we solve the value as CT is found to be 17.31 into 10 to the power 5 amperes per meter. So this is the value of HCT which is determined by this equation, keeping the values of HC0 and TC. Next important question which is frequently asked in examination is on critical magnetic field and critical current. So now in this question, critical magnetic field at 0 Kelvin is given. A bit of work is easy. 6.5 into 10 to the power 3 ampere per meter. And for our God grace, TC is also given 7.18 Kelvin. Now at what temperature critical field would drop to? Magnetic field is given, at CT is given 4.5 into 10 to the power 3 ampere per meter. We need to determine the value of T. This question we have already discussed. This was the very first numerical. Again, we will write the standard formula. So here we have to determine the value of this T. So when you will keep these values, the value of T is found to be 3.98 Kelvin when you substitute these values. Now next part of this question is diameter of the wire is 2 millimeter, which means radius will be 1 millimeter and in standard rotation it will be 10 power minus 3 meter. What is the critical current density at that temperature? We all are aware critical current is 2 pi r HC, where this HC is HCT. And your current density is current upon area. So current is 2 pi r HC and area is pi r square. So the formula will be 2 HC by r. HC value is given 4.5 into 10 to the power 3 divided by r 10 to the power minus 3. So this question is quite easy. The value will be 4.5 but twice will be 9.0 into 10 to the power. This power will be positive 6 ampere per meter square. What students generally do is that they write here ampere per meter. Ampere per meter is the unit of your magnetic field. So as it is current upon area, it should be ampere per meter square. You need to remember. So these are certain very important, frequently asked numericals in AKTU. These numericals being asked repeatedly in the past 2 years in odd and even semester. References for this numerical are taken from the standard books by Supil and Arthur Weiss. Thank you so much for patiently watching this lecture.